Once a star has left the protostar stage and nuclear fusion has begun, it starts its life as a main sequence star. As it gets older, after billions of years, it grows up and becomes a red giant. After a long nuclear fusion workout using a number of elements for another few billion years, it will lose the weight around its core in one of two ways. If it works hard enough, it will lose the gassy weight in the most painless way possible, and it will be a hot little thing. We call this the white dwarf stage. But, God forbid, if it overworks itself during its long haul as a red giant, it will explode under the pressure. Although the little ball of neutrons that results is typically only about 10 kilometers long, this neutron star is full of surprises. Let's explore the facts.
Upon reaching a certain density, a main sequence star begins to fuse hydrogen into helium. When this occurs, energy gained by gravitational contraction subsides, and fusion takes over to become the main source of energy for the star. The star will remain in this state for the majority of its life until the hydrogen in its core is expended.
Main sequence star, you've changed!
I'm getting older and my core is expanding with age as I fuse new elements. Red giants form from main sequence stars that range from 0.3 to 8 solar masses. When the main sequence star exhausts the hydrogen fuel in its core, nuclear reactions can no longer continue, so the core begins to contract due to its own gravity. This brings additional hydrogen into a zone where the temperature and pressure are adequate to cause fusion to resume in a shell around the core. The higher temperatures lead to an increased reaction rates, enough to increase the star's luminosity by a factor of 1,000 to 10,000. The outer layers of the star then expand, officially beginning the red giant phase of a star's life. As the stars expand, the energy produced in the burning shell of the star is spread over a much larger surface area, resulting in a lower surface temperature and a shift in the star's visible light output toward the red end of the spectrum. Once the red giant has run its course, the remainder of the star's life could go one of two ways.
I feel so much lighter after losing all that weight. A white dwarf is the final stage of the evolution of a star that is between 0.7 and 1.4 solar masses. White dwarfs represent a stable phase in which stars of less than 1.4 solar masses live out the rest of their lives. They're characterized by a low luminosity, a mass close to that of our Sun, and a radius only the size of the Earth. White dwarfs have low luminosities. Because of this, they can only be observed within a few parsecs of Earth. When a white dwarf exceeds 1.4 solar masses due to it accreting matter from a nearby star, the white dwarf rapidly reignites, creating a large nuclear explosion on the surface of the star, or standard candle, that we call a nova.
When the star is burning, the heat in the star pushes out and balances the force of gravity. When the fuel is spent, there is no energy to counteract the force of gravity. The star collapses in upon itself. Stars about the same mass as the Sun become white dwarfs, which glow with leftover heat. Stars that have about 3 times the mass of the Sun compact into neutron stars. A star with a mass greater than 3 times the Sun's gets crushed into a single point, which we call a black hole.
When a star 10 times more massive than the Sun expands, the helium becomes its core, and the nuclear fusion cycle continues. As fusion continues, the helium core becomes a shell. The cycle continues until the core is iron. Without any source of heat to balance out the gravity, the iron core collapses into a high-density core. This high-density core resists further collapse, causing it to fall inward in a manner that it seems like it's bouncing off the core. The sudden core bounce produces a Supernova explosion. For a brilliant month, a single star burns brighter than a whole galaxy of billions of stars. Supernova explosions inject carbon, oxygen, silicon, and other heavy elements up to iron into interstellar space. They are also the site where most elements heavier than iron are produced.